A system of linear equations is when you have two or more linear functions that have the same two variables. So in both cases, we could change them to y equals mx plus b, and then you could graph them. What we're looking for is we're looking for the point that's on both of the graphs. So in this one, can you see that you could rearrange it to be y equals negative x plus 5? And this one you could rearrange to be x minus 1 on the left equals y, or y equals x minus 1. And from the chapter that we just did, that means we have one graph. I'm going to change the color of this to be green. Almost. Did it? You see green? Okay. I still. Okay. Let's try that again. Supposed to change this to green. Yeah. Oh, and it just shut down everything. That's a problem. So if you wanted to graph both of these, the green line has a y-intercept of 5. Are you guys getting really good at graphing these y equals mx plus b ones? And a slope of negative 1 means down 1 over 1, down 1 over 1. And the green line looks like this. The blue line has a y-intercept of negative 1 and a slope of positive 1, up 1 over 1, up 1 over 1, up 1 over 1. What is the one point that both graphs have? Three comma 3? No, it doesn't quite work for those. 3 comma 2. What happens in here if I plug into the blue graph? When x is 3, what's y? 3 minus 1? 2. If I plug in 3 in the green graph, what's negative 3 plus 5? 2. So there's only that one point that's on both of the graphs. And that's what we're going to be looking for. Okay? We say that that solution of that graph represents the coordinates that satisfy both equations. And the only coordinate, when we drew our graph, we could kind of see where that was, are the coordinates 3 comma 2. So graphically, this represents the point of intersection between the two lines. So we could make, and one of the things that we're going to be doing in these kind of questions is saying stuff like, a bag of chips and a chocolate bar cost $5. That's my first equation. X is my bag of chips, Y is my chocolate bars. X plus Y equals 5. A bag of chips and a chocolate bar costs $5. The chips are $1 more than the chocolate bar. So if I subtract the two of them, chips minus chocolate bars, I should get $1 because that's the difference between them. And so you can take your situation and make two equations. And if you can make two equations, well, one thing that we just did is you could graph both of those equations and find out where they intersect. So in this unit, we're going to be looking at what are the different techniques that we can use to find that, so that you could say, oh, if chips and a chocolate bar cost $5 and there's a $1 difference between them, one is $3, the other is $2. That's the only way it would work. So we've already figured out that this has a solution when x is equal to 3 and y is equal to 2. We write the solution as a coordinate. 3, 2 is the solution. If we substitute these values into both equations are true. So that shows, 3 plus 2 is equal to 5 and 3 minus 2 is equal to 1. We can verify that that point works for both of them. And in fact, if we think about the graphs that we drew, those are the only points that work. So as a warm-up, try to figure these ones out. What numbers would work? And at this point, I don't care if you have developed a complicated 8-page technique or guess and check and get it right. Just see if you can find points that work. All right, for the first one, be able to get 4 and 2. And so we would write that solution as a coordinate 4, 2. Your x coordinate goes first, your y coordinate goes second. Okay? You could verify it. Is 4 plus 2 6? Yes. Is 4 minus 2 2? Yes. Second one was a little bit more difficult. 3 and, there was a negative involved. 3 and negative 4. Okay? As soon as that negative came involved, all of a sudden you're guessing and checking. I noticed for a lot of you took longer, right? What would happen if I changed the answers to fractions? Okay? What about fractions and negative fractions? Okay? That would have been guessing and checking probably much, much longer. So we need to develop techniques so that it isn't longer, so that it could be the same even if they were crazy fractions or crazy decimals or negatives or positives or whatever. Sometimes we'll even get solutions which are square roots. One of the answers is a square root and the other one isn't. I'm telling you, guessing and checking, you would like, right? On the first one, you're like, oh, something minus something is 2. You probably went to like 5 minus 3 or 4 minus 2 right away. Nobody decided to do something crazy with, oh, what if x was the square root of 10? What would y be so that I subtract and get 2? No, your brain doesn't do that. It goes to easy numbers. And the problem is if you only go to easy numbers when the answers are not easy numbers, you can't do it. Okay? And one of the reasons we develop all of these skills in algebra is because in most real-life situations, the numbers aren't easy. Right? You become a biologist and you study dolphins' migratory patterns or something, and you want to find out the average speed that they're going. And they're like, oh, man, they are not traveling at a nice speed. You just want to tell the dolphins, please go 12 kilometers per hour, because that makes my math a lot easier. But you guys keep going 11.876 kilometers per hour, and my math is more difficult. Well, unfortunately, most real-life situations, the numbers aren't nice. So we need to not only develop techniques for nice numbers, but develop techniques that work for any numbers. So the first technique that we are going to look at, which we kind of peeked at already, is graphically. This connects to the unit that we just finished. We got really good at graphing lines. Or if we didn't quite get really good at them, we will get really good at graphing lines before Thursday when we have our test. That's the plan. Okay? So the solution of a system of two linear functions is the point of intersection. In other words, if we can graph both lines and a point magically appears, I don't know if it'll be that magic, But if a point appears where they intersect and you can find the coordinates of that point, then you will have found the solution. So let's look at an example. The question is saying, is 4, 0 a solution to the following system? And we want to solve it graphically. I'm going to put a blue box around this equation and a green box around this equation, so all of the work that I do with the first equation, I'll do in blue. So in the blue equation, can you see that you could rearrange this to be y equals negative x plus 4? And negative x plus 4 would have a y-intercept of 4 and a slope of negative 1. When you have the slope, right, our slope is negative 1, which I can write as a fraction, negative 1 over 1. That means a rise of negative 1, a run of 1, down 1 over 1. The other thing you should know about your slopes is when you have a negative slope, it's going down from left to right. So sometimes I just say, if I go up 1, I would have to go 1 to the left in order for that to keep going down. So you can draw a whole bunch of points using your slope. And the reason I'm labeling a whole bunch is to see where do things intersect. Whoa. Nice straight line through all of those points. Our next equation, I could rearrange the equation, move the 8 over to the left, move the y over to the right. That means that y is equal to 2x minus 8. And my slope in this one is 2, which I can write as a fraction, as 2 over 1. Because I changed it to y equals 2x minus 8, it's in y equals mx plus b form. That means that my y-intercept is at 0, negative 8. My slope is 2 and it's positive. So if I go up 2 and over 1, it would have to be in this direction. Up 2 over 1, up 2 over 1, up 2 over 1. And we can see from the graphs that they intersect here. That point is at 4, 0. What was our original question? Is 4, 0 the solution to this equation? We can say yes. We can say yes because the graphs intersect at this point. So it is the solution. What's another way we could tell if it's a solution or not? If it works. I would probably recommend that as the faster way, right? Plug in 4 for x, 0 for y, okay? Make sure that you remember that your x coordinate is always first, your y coordinate is always second. Is 4 plus 0 4? Yep, last time I checked. Is 2 times 4 minus 0 8? Yes. So since the point works for both equations, we know it's a solution. That would be faster than graphing it. But right now we're looking at developing the technique of graphing to find a solution. So we graphed it as well to show that they intersect at that point. But the fastest way to find out if something is a solution is to plug it in and verify, does the point work or not? But since this is also good practice for our chapter test coming up where we have to graph lines, it is good to practice rearranging these equations into y equals mx plus b, right? It's good to know plugging things in. Does this one work? Does 3, negative 4 work for the first equation? Is 2 times 3 minus a negative 4 equal to 10? Yes, it works for the first equation. Does it work for the second equation? Is 2 times 3 minus 3 times negative 4 equal to 14? No. So it isn't the solution to this equation, but now we'll look at it graphically as well. So I'm going to color code things again. What color did I use first last time? Blue. The first one I'll make blue. The second one I'll make green. If you have a pencil and a pen, you can do your work that way. One in pencil, one in pen. Or you can put a little number equation 1 and a little number equation 2 so that you can see which work goes with which. So for equation 1 in blue, can you see that I could get the y by itself by subtracting 10 on both sides and adding y to both sides? Rewriting this means that this is 2x minus 10. My slope is 2, which is 2 over 1. My y-intercept is negative 10. Up 2 over 1, 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 and so on. And my green line if I subtract 14 on both sides and add 3y to both sides, I get y by itself. How would I get y by itself? Divide by 3. So then I get y equals 2/3 x minus 14 over 3. Excellent. What's not nice about this line? The y-intercept is a fraction. It's okay, it's actually not bad if your slope is a fraction, because here going up 2 over 3 isn't bad. But starting off with negative 14/3 as a y-intercept is a little bit not nice. It's more than a little bit not nice. It's like, yuck. Question. Can you find a nice point on the green graph, which was 2x minus 14 equals 3y? Or what was it originally? 2x plus 3y, 2x minus 3y equals 14. If you can find one nice point on the graph, then we could use our slope to find other points. So I want you to do some mental math, plug in values for x and plug in values for y to get a nice point for 2x minus 3y equals 14. And there are some strategies to make it even better, but let's see if what... Yep, you found one? 13 for x, 4 for y. Does that work? Check it out. Is 13 times 2, which is 26, minus 3 times 4, which is 12. Does that make 14? Is 26 minus 12 14? Yes. So there's one nice point. But like you said, it's a nice point that doesn't fit on my graph. Found another one. 7 comma 0. Oh, very nice. When x is 7 and y is 0, that one works. Does that one fit on my graph? Yes. Okay, so I know that 7 comma 0 fits on my graph. What was my slope? 2 over 3. Is that a positive slope or a negative slope? Positive. So I could go up 2 over 3, or I could go down 2 over 3, down 2 over 3, down 2 over 3. My slope is positive, so it needs to go up from left to right. Does it look like there's a point where they intersect? What is the coordinates of this point on our graph? 4, negative 2. So now I want you to verify, does that point work for both equations? When x is 4, y is negative 2. So let's look at our original equations. What's 2 times 4? 8 minus a negative 2. Does that make 10? Yes. And 2 times 4, which is 8, minus 3 times a negative 2, which would be plus 6, is 8 plus 6, 14? Yes. So the solution is 4, negative 2. The question was, is 3, negative 4, and I'll put that on in purple. The original question was, is 3, negative 4 a solution? The answer would be no, because 3, negative 4 is not on both graphs. It's not on the intersection of the two. In order for it to be a solution, it needs to be on both equations. Graphically, that would mean where the graphs intersect. And 3, negative 4 is only on the blue graph, not the green graph. So when we verify it, it worked for one, but it didn't work for the other one. Some strategies for finding nice points. One of the things that I did here was think about even and odd numbers. When you add or subtract two even numbers, you always get an even number. When you add an even and an odd number together, you'll always get an odd number. So I noticed that this 14 is always going to be even. I noticed that 2 times a number is always going to be even. Does that make sense? So what do I want this number to be? Well, an even minus an even number will be even. I needed that to be even. So if you just picked a random even number for y, 2. 3 times 2 would be 6. Add the 6 to the other side, or 2 times something minus 6 is 14. What minus 6 is 14? This would have to be 20. X would have had to have been 10. That would have found you a nice point. In fact, you could have used any even number, like 4, you would have got 13. Only problem with 4 is it went off. But if you went backwards, 0 would have got you 7. Or negative 2 would have worked as well. So an idea of how you can look at the equation and think about what might work out well. So the first two questions asked us to find equations that would work. Our last question here says to solve. So up till now, you've been using guessing and checking, but how does the graphing help us solve it maybe a little bit quicker than guessing and checking? Again, I will make this equation 1 and this equation 2, 1 in blue, 1 in green. For the blue one, I can get y by itself by moving the x to the other side. Tells me it has a slope of negative 1 over 1 and a y-intercept of $12. Ooh. It's going to be going down from left to right, down 1 over 1, and then finally I get back on So with the graphing technique, we like to label a lot of points because our hope is that when we graph our other equation, it works out nicely to hit a point perfectly between the two graphs. For our green equation, I can move the 2 over to the left and the y over to the right. That gives me y equals x minus 2, which has a slope of 1, or 1 over 1, a y-intercept of negative 2, slope of 1, oh, and happiness. There was a point where they both intersected very nicely. Where is that point? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 7, 5, it appears to be. So we do a quick check. Is 7 plus 5 equal to 12? Yes, it works on the blue one. Is 7 minus 5 equal to 2? Yes, it works on the green one. So we know that 7, 5 is the solution. Just labeling 7, 5 wouldn't be enough on an exam or a test because you need to show that not only do you know where they intersect, but you know that the intersection is the solution. Right? Because if I was looking at your graph, I'm like, okay, they also labeled this. Do they think this is the solution? Do they think this is the solution, or do they think this is the solution? How do I know which point they think is the solution? So a statement at the end clearly stating, yes, I know that where they intersect is the solution, so 7, 5 is my solution. Okay, I'd like you to try these next two. Can anybody see or predict a problem with the graphing technique? Okay, so here's our solution here. It worked out nicely to be a nice point. What if it doesn't work out nicely to be a nice point? Like, or if it's way off the graph, or you know, if the solution was 325, 283. Oh. Right? You could be graphing for a very long time. So the graphing technique is nice for certain examples, but we're going to learn other techniques that'll work even better later on. The first skill that I see that a number of you are having some trouble with is this idea of changing to y equals mx plus b. Okay? So there's my blue equation, there's my green equation. The reason we change it to y equals mx plus b is because then we know one point, your y-intercept is a specific point, and you know your slope. And once you know one point and a slope, you can graph a whole bunch other points really quite quickly and quite easily. So for our blue equation, if I want to get y by itself, I'm going to add y to both sides, which gives me y equals x minus 1. I now know that my slope is equal to 1, the coefficient, which I can write as 1 over 1, and my y-intercept is negative 1. So I can label that y-intercept on my graph as negative 1 comma 0. And using rise over run, I have a positive slope, up 1 over 1, up 1 over 1, rise over run over and over again, and get a bunch of points. And I can draw my blue line. My green equation, the y is already positive on the left-hand side, so I'm going to subtract 2x on both sides. That tells me my slope is negative 2. My y-intercept is negative 4. So there's my y-intercept. Oops, my first y-intercept, it looks like I labeled wrong the x coordinates first, then the y. 0 comma negative 4. A negative slope means that it's going down from left to right. So down 2 over 1, over 2, up 1. And I could draw more points if I wanted to, but this is enough to find out where they intersect. And my solution is at negative 1, negative 2. You can plug in your solution into both equations to see that they work on both. That way you know that they're right. If your solution doesn't work on both, then it means you have to recheck your math, because it should work for both of them. Finally, the last equation here, again, we're going to rearrange both of these equations to y equals mx plus b. For your blue one, I'll move my y to this side, subtract 2 on both sides, so I get y equals 3x minus 2. Slope is 3. Y-intercept is negative 2, up 3 over 1, up 3 over 1, up 3 over 1, down 3 over 1, down 3 over 1. So we can get a bunch of points quickly on our green equation. Subtract 2x on both sides. And you get negative 2x minus 12. So that means our y-intercept is at negative 12. And a slope of negative 2 means that it's going down 2 from left to right, so we can go up 2, back 1, up 2, back 1, up 2, back 1. And that's enough to find out that our solution is at negative 2, negative 8. Now your graphing calculator has a program built in to graph lines, and if you graph both lines, it has a program built in to find out where they intersect. So that's what we're going to look at in the last bit of the lesson today, is how you would do this with your graphing calculators. You have to still rewrite the equations in y equals mx plus b. So what we're going to do is we're going to use these equations that we rewrote, 3x minus 2 and negative 2x minus 12, and see what that looks like in your calculator. So the first thing on your calculator is you're going to push y equals in the top left-hand corner. If you have any other equations in there, you can clear them by hitting the clear button. Our first equation was 3x minus 2. So you type 3. The x button is right beside the alpha button. So 3x minus 2. That's your first equation. Your second equation was negative 2x minus 12. The negative sign is beside the decimal here. Negative 2x subtract 12. It is important that you know the difference on your graphing calculator between the negative sign and the subtract sign. So we need to do negative 2x minus 12. And when you hit graph, it graphs both of those equations exactly the same as we graphed them. And after they're both graphed, you can see that the graphs intersect on your graphing calculator. Everything you want to calculate with graphs is above your trace button. So you can go second, and above trace it says calculate, so second and then trace. And then it lets you calculate a bunch of different things. What we want to find is number 5. Where do these intersect? So when we push enter, it says, which one do you want to be your first curve? It's on the first curve, push enter once. Which one do you want to be your second curve? It goes to the second curve, you push enter again. Would you like to guess? Not really. Push enter again. And it tells you they intersect at negative 2, negative 8. So you can use your graphing calculator as a way to check to see if your answers are right. So your homework is listed at the bottom there. We have 7 minutes left. You can work on that.